right, these notes are going to be on Taylor and Maclaurin polynomials in series. So first, before we move on to the new stuff, we're going to start with something that we hopefully will recognize and feel comfortable with. So they're going to ask us to find the equation of the tangent line for the function f of x is sine x at x equals 0. And then we're going to use it to approximate a value of sine. So I'm going to say if f of x is sine x, then f of 0 is sine of 0, which is 0. So that means that the point that we're using, that we're finding the tangent line for, is the point 0, 0. The first derivative of sine, or the derivative of sine, is just cos. And if I evaluate the first derivative at 0, cos of 0 is 1. I just printed something. I don't know if you guys can hear that. It's my printer. So if we want to go ahead and write the equation of the tangent line, we would say y minus 0 is 1 times x minus 0. And we can go ahead and simplify that and just say y equals x is the equation of the tangent line. So if I want to go ahead and use that tangent line to approximate sine of 0.2, then I would say y of 0.2 equals x. I'll plug in the 0.2. And so that means that sine of 0.2 is approximately 0.2. All right. And if I want to see if this is an overestimate or an underestimate using some calculus, then I just have to picture the sine curve and see what's happening there, if it's concave up or if it's concave down. So if I think of the sine curve, it looks like this. And so our tangent line was right there at 0, but which is in between concave up and concave down. But what we were approximating was 0.2, which is slightly to the right, which would definitely be part of the curve that is concave down, so the tangent line is above the curve right there. If we had been approximating negative 0.2, it would have been another story. But positive 0.2 is a little bit to the right of 0, which means the tangent line was above the curve that was concave down, and so that means that this is going to be a little bit of an overestimate. All right, so the equation of the tangent line is a very simple version of what we call a Taylor polynomial. So when we first looked at tangent lines and like linear approximations, we used the tangent line to help us approximate values that were near this point of curves that maybe we didn't have the whole curve, so we couldn't plug it into the calculator and check. Maybe we were doing a calculator inactive problem, so we couldn't check the actual value. So the tangent line was a straight line, and anywhere we were on a point that was like close to where the curve intersected that tangent line, then we could get a reasonably accurate approximation of the function at that value. So Taylor polynomials have higher degrees, so a second degree or a third degree or a fourth degree, which means we can get a polynomial curve that kind of follows a function, which would mean that our approximations are going to be even better than they are with tangent lines, so that even if we're plugging in an approximation, let's say the point is at 0 and we're plugging something in at 4, we might still have a really accurate approximation even though the point is so far away. So here is a picture of Brooke Taylor, who is, the Taylor polynomials are named after him. So here's the formula and here's how they work. And it seems really crazy, but this beginning part, if you can see this part right here, this is actually the equation of a tangent line right here. So you can see this is the slope at 0. This would be x minus 0. And this part right here is kind of like if we took this 0 right here and added it onto the end. So this first part we've actually dealt with before, where we said the slope times x minus whatever the x coordinate was, and there's the y coordinate. And so what we're going to do is we're actually going to kind of keep this pattern going. So we're going to say the second derivative evaluated at that 0, and then x minus 0 squared. The third derivative evaluated at 0, x minus 0 cubed. So you can kind of see that the pattern is the same. We just have this extra part where we have these factorials added in there. And of course, we don't always have an x value of 0 when we find our tangent lines. We really could have had any x value that we wanted. And so that's why it says C, because we could use lots of different values for our tangent lines. Or in this case, we're going to call them Taylor polynomial. Because we don't just have lines, now we have polynomials. So the way that this is phrased and the way it's going to be phrased in the prompts that you have on your worksheets is it's going to say the nth degree Taylor polynomial for f centered at C. So when they say f, they're talking about that function f of x. When they say centered at C, they're talking about that value of x that you're evaluating it for. So plugging in x equals 0 as a way of kind of like figuring out where your tangent line starts, or in this case, figuring out where your polynomial approximation will start. And then the nth degree is just they're telling you how many pieces you want. So our tangent line was a first degree Taylor polynomial because it had x to the first power, it was linear. But if we wanted an x to the second power Taylor polynomial, then we would just use this part. If we wanted an x to the third, so a third degree, we would want that part. So a first degree Taylor polynomial is a tangent line, which is what I had just said. And then this stuff right here just counts as the coefficient. So like I said here, the f prime of C was that 1. That was the coefficient for the parentheses. And if it's confusing to you that the 2 factorial and the 3 factorial are there, but there's no 1 factorial, that's because you can have a 1 factorial and it doesn't make a difference because it just equals 1. And back here you can go back and say 0 factorial and it still doesn't make a difference because it's still 1. So technically those could have been there. All right, so then we have a picture here of Colin Maclaurin, and he has the nth degree Maclaurin polynomial, which is really just a Taylor polynomial, specifically when we're talking about using an x value of 0. And so you can see that his f of 0, f prime of 0, and then it doesn't say x minus c, because just like what we did up here, x minus 0, we just simplified and we called it x. And that's exactly what a Maclaurin polynomial does. So basically it's a specific case of a Taylor polynomial, and when you read this in a problem, you'll be like, oh, I just need to use x equals 0. And this should say centered at 0, not centered at C. I probably copy-pasted and missed that. All right. So one thing we have to keep in mind when we write this is that when we write our polynomial approximations, we're going to say like P6 of x or whatever, and we're going to write a squiggly equal sign to show that that polynomial is an approximation of the function. It's not exactly the same, because technically some decimal places would be off, even if they are like, you know, the 15th decimal place or something. Okay, so let's go ahead and actually do some examples of this. So example 2 says find the Maclaurin polynomial. So they're telling us right now that we're going to use x equals 0, and they want a first degree, which is a tangent line, and a third degree, fifth degree, and seventh degree. And then they want us to use the 7th degree polynomial to approximate sine of 0.2. So when we approximated sine of 0.2 with example 1, we got a decimal that's probably reasonably close if you round. But when we go and we use the 7th degree polynomial, we should get very, very close to the actual value. So what I'm going to do first is go through and to be able to use the formula for this, if I'm doing a 7th degree, like an x to the 7th, that means I'm going to have the 7th derivative to plug into the problem, which means I've got quite a few derivatives to find. So I'm going to say that the original function was sine of x. The first derivative is cos. The second derivative, cos is negative sine. The third derivative is negative cos. The fourth derivative would be positive sine. The fifth derivative would be cos. The sixth derivative would be negative sine. And then the 7th derivative would be negative cos. Okay, so then what we need to do is we need to find all of those evaluated at 0 because it says f of 0, f prime of 0, f double prime of 0, f triple prime of 0. That's what we're using. So f of 0 is 0, f prime of 0, cos of 0 is 1, yep. F double prime of 0 is 0, f triple prime of 0 is -1, the fourth derivative evaluated at 0 is 0, the fifth derivative evaluated at 0 is 1, the sixth derivative evaluated at 0 is 0, and the seventh derivative evaluated at 0 is -1. So we're going to say the first degree Maclaurin polynomial is f of 0 plus f prime of 0 times x. So that is going to be 0 plus 1 times x, which is what we found for example 1. It was just y equals x. The third polynomial, Maclaurin polynomial, for sine x is going to be 0 plus 1x plus 0x squared over 2 factorial plus -1, so I'll say minus 1x to the third over 3 factorial. So if you guys want to kind of simplify these off to the side, you can. We could say the first one's just x. The third one is going to be x minus x to the third over 3 factorial. All right, the fifth degree Maclaurin polynomial is 0 plus 1x plus 0x squared over 2 factorial minus 1x to the third over 3 factorial plus 0x to the fourth over 4 factorial and then plus 1x to the fifth over 5 factorial. So we've got 0, 1, 0, -1, 0, 1. And then for the seventh, we've got 0 plus 1, 0, minus 1, 0, plus 1, 0, minus 1. Whew. Wasn't that obnoxious? Okay, so now it wants us to evaluate this at 0.2, and it wants us to graph the original function and the polynomial. So what I'm going to do is, instead of plugging that polynomial in twice, I'm just going to go ahead and graph it. So I'm going to do 1x minus 1x to the third divided by 3 factorial plus 1x to the fifth divided by 5 factorial minus 1x to the seventh divided by 7 factorial. And I'll go ahead and make my window, I'll do -1 to 1. That was really exciting to watch. Okay, so now I'm going to go ahead and evaluate this at 0.2. And so I'm going to say this is approximately 0.198666933, and so that's pretty close there. So now if I go ahead and right after this, I'm going to go ahead and graph sine x. The approximation is so close to the actual graph, we can't even see the difference right now. That's really interesting. So let's go ahead and get out of the screen real quick. So I'm going to show you guys something. If we do sine of 0.2 and we subtract off, I'm going to go into vars, y1, that function that I just used, 0.2. If I subtract those values from each other, this is the difference of the actual evaluation minus my approximation. So that means that my approximation was 0.000000011 zeros 14 off. That means that if we type in sine of 0.2, all these decimals would be the same as, and hold on, let me type mine again. Sometimes when you use the graph to get it, it doesn't do a very good job. So if you guys can see that my approximation using the Maclaurin polynomial and then the actual sine graph, they're very close for the first several decimals there, which is kind of neat. Mind blown? Anybody? No? Okay, so if we want to see this a little bit better, I'm going to make this window go further. So let's say, I'll maybe just go to 10, from negative 10 to 10, so you guys can kind of see. That might take a while to graph. Oh, I should have changed that. That's okay. Okay, so what you guys saw was you saw the Taylor polynomial first, or the Maclaurin polynomial first, and it went down like this, and then it kept going down. And then after that, you saw the sine graph come up. So what you can see is that the Taylor, and I'm going to go ahead and get rid of the sine graph really quick. You can see that the Maclaurin polynomial, or the Taylor polynomial, was a really accurate representation, but only for that little part of the graph, not for the whole thing. So it's kind of that same idea as like a tangent line approximation, where the tangent line is only accurate for like a short area, but the Maclaurin polynomial or Taylor polynomial just makes it so there are more values that are accurate, which I think is really interesting. I hope you guys think it's interesting too. Okay, so next they want us to find the Maclaurin polynomial of degree 6, and we're doing this for cos. So this is going to feel kind of like the last problem we just did, or derivatives at least. So the first derivative is negative sine, the second derivative is negative cos, the third derivative is positive sine, the fourth derivative is cos, the fifth derivative is negative sine, and the sixth derivative is negative cos. And it's a Maclaurin polynomial, which means that we're plugging in 0. So f of 0 is 1, f prime of 0 is 0, f double prime of 0 is negative 1, 0, sorry, that'd be 1, 0, and negative 1. Okay, so this one is not as terrible as the last one because it's not asking us to find all of them, just the sixth. So I'm going to say the sixth degree Maclaurin polynomial centered at 0 is going to be 1 plus 0x minus 1x squared over 2 factorial plus 0x to the third over 3 factorial plus 1x to the fourth over 4 factorial plus 0x to the fifth over 5 factorial minus 1x to the sixth over 6 factorial. And so we're going to approximate the value of cos of 0.1 using correct notation. So I'm going to say cos of 0.1 is approximately the sixth degree Maclaurin polynomial evaluated at 0.1, which is approximately, we can go ahead and type this in. So I'm going to have 1 minus 1 times 0.01, no, 0.1 to the second divided by 2 factorial plus 1 times 0.1 to the fourth divided by 4 The reason why I'm putting this in parentheses on the bottom is because I want the factorial to go to the 4 only, not the whole piece. And so that's why I'm typing it that way. Okay, and so this is 0.995004163. And if I want to find how far away the calculator evaluation is, I would say cos of 0.1 minus, and then I can go up here. I put a parenthesis there. I'm going to go up there and grab what I plugged in. And so 2.5e to the negative 13. So again, the 6th degree polynomial is going to give me a pretty accurate number, especially when 0.1 is so close to 0. Kind of as we could see before when we graphed it, it's very close. All right, example 4 says find the Taylor polynomial of degree 6 for f of x equals ln x, evaluated at c equals 1 this time. Well, not evaluating, we're evaluating 1.1, but we're centering it at 1. So I'm going to say f of x is ln x, f prime of x is 1 over x, which I'm going to write as x to the negative 1, just to make my life a little bit easier. F double prime of x is negative 1 x to the negative 2. F triple prime of x is 2 x to the negative 3, degree 6. The 4th derivative is negative 6 x to the negative 4. The 5th derivative is 24 x to the negative 5. And the 6th derivative, 24 times negative 5, is negative 120 x to the negative 6th. Okay, hold on, I'll get my note. Okay, sorry guys, whenever I don't have my notes, I always make little mistakes. Okay, so we have the original function evaluated at 1. Ln of 1 is 0. The first derivative evaluated at 1 is just 1 over 1, and so that's 1. The second derivative evaluated at 1 would be negative 1 over x squared, so that's negative 1 over 1 squared, which is negative 1. That would be 2 over 1 to the 3rd power, so that's 2. Negative 6 over 1 to the 4th power. Oh, I wrote 1 twice. 1, 2, 3, 4. All right, 5th derivative evaluated at 1. 24 over 1 to the 5th power. And then 6th derivative evaluated at 1. Negative 120 over 1 to the 6th power. Okay, and I don't know if you guys recognize these yet or not, but these are actually factorials. So this is 2 factorial, 3 factorial, 4 factorial, 5 factorial, which is kind of interesting. Okay, so let's go ahead and we're going to write the 6th degree Taylor polynomial. And so first I have f of 1, which we said was 0, plus f prime of 1, which was 1, times x minus 1 to the 1st power, and I'll go ahead and put over 1 factorial. And then we have minus 1 times x minus 1 to the 2nd divided by 2 factorial. And then I have plus 2x minus 1 to the 3rd divided by 3 factorial minus 6x minus 1 to the 4th over 4 factorial plus 24x minus 1 to the 5th over 5 factorial minus 120 x minus 1 to the 6th over 6 factorial. Oops, sorry, I moved that. All right, speaking of things that are not fun to plug in, let's plug this in. All right, 1 times 1.1 minus 1 to the 1 divided by 1 factorial. I'm just going to leave that. Minus 1, 1.1 minus 1 to the second divided by 2 factorial plus 2 times 1.1 minus 1 to the third divided by 3 factorial minus 6 times 1.1 minus 1 to the fourth plus 24, 1.1 minus 1 to the fifth divided by 5 factorial minus 120, 1.1 minus 1 to the sixth. I'm like terrified right now that I have a typo in here somewhere and this is not going to work out because I typed too fast. Okay, just going to check those. Minus 120, 5 factorial 5, plus 24, yep. 4 factorial 4, 6, yep. 3, 2, yep. 2 factorial 2, and 1, yep. Okay. All right, so I get 0.0953. And if I want to double check that, I can go ahead and say that this is approximately ln of 1.1. But if I want to just verify for myself, I can see those decimals are very, very close to each other. You can kind of see back here where they start to change. Okay, I'm going to do one more problem, even though this video is getting kind of long, because it's going to take us a while to do the notes in class too. So there's no winning here. Okay, so it says, suppose the g is a function which has continuous derivatives. They're saying that because, if you guys remember back to the notes, to have a certain number of Taylor polynomials, we have to have the derivatives for all those pieces, so that's why they said it like that. They said that g of 2 is 3. I was reading it, you couldn't even see. G of 2 is 3. G prime of 2 is negative 4. G double prime of 2 is 7. G triple prime of 2 is negative 5. So we can see that we have a Taylor polynomial. I know it's a Taylor because it's evaluated here, or it's centered at 2, not at 0. Degree of 3, that's why there's 3 derivatives. And so we have to go back and look at the Taylor polynomial and make sure that we do this right. So f of 2 is what we're going to write first. So we're going to say the third degree Taylor polynomial is going to be 3 plus, minus, because it's a negative, minus 4, x minus 2 to the first, divided by 1 factorial if you want, plus 7 times x minus 2 to the second, divided by 2 factorial, minus 5 times x minus 2 to the third, divided by 3 factorial. So if all they want is the polynomial, there we have it, we've written the polynomial. Now if they wanted us to take g of x and evaluate it at some value that's kind of near 2, we could do that with relative certainty that we have something that's pretty close to the actual value of that function, even though we have no idea what that function is, which I think is kind of cool.